How we define color. We can define it more than one way. When we talk about what is color, well, what exactly is it? We can start with that it's a certain kind of light. You'll see a little bit that without light we don't have any color. That's one of the key ingredients for having color. It's also the light's effect on the human eye. It's the result of this effect in the mind of the viewer. And really, when we say we see a certain color, that's what we're talking about. Is what's it look like? What are we perceiving it as in our mind? What we perceive, and that, when it gets down to it, is the most important. As we go through this class, we'll talk about instruments, pretty sophisticated, expensive instruments that we use to measure color. But when you really get down to it, the most important interpretation is what we see, or what the customer sees if we're selling color, because that's how people buy it. They buy color by what it looks like, not what the numbers say. Although there's a lot of companies that like to use numbers, there's no subjectivity to it. If it says it's out of spec, it's no good, and if it's in spec, it's good. As we go down a few classes from now, we'll see that it doesn't always match up with what we see visually. So we have to always go with what we see visually. So color is a matter of three, and we'll use this number 3 when describing colors a lot. So color is what we see. It's the result of the physical modification of light, first thing, by an object, second thing, and as observed by the human eye in the interpretation of the brain. So if you don't get anything else out of this class by the end of the term, you'll hear it enough times where you should remember that. What it takes to have color, there's 3 things: light, an object, and an observer. And you can bet that'll be on more than one quiz or test, and if you get that one wrong, then I throw you out of class. That's the real basic truth, if you want, of this class. Right, so our model for seeing color. We're going to talk about color in terms of a model. In science, we like to model physical phenomena, mainly mathematically. That's how kind of the language of science is mathematics, and we'll talk about how we do that. To describe something like seeing color is very, very complicated. We can't do it exactly like it really happens in nature. It's just too complicated. So we try to come up with a simple model that represents how that works. So throughout this course, we will describe color using a mathematical model that incorporates the following 3 necessary physical components to perceive or define color. Color results from the interaction of a light source, an object, and the eye and brain or visual system. We got to have some kind of light source, something we're looking at, say what color it is, and then some type of detector. The most common way we do it in everyday life is like this. We're outside the sun, and we use our eyes and brain. When we get into the laboratory, we can replace the light source in our eye and brain with an instrument, spectrophotometer in the computer. That does it also. It doesn't do it exactly like we do it, but it kind of simulates. You've got to have a light source, object, and observer. You can either have an eye-brain combination for an observer or an instrument-computer combination for it, but that has to be present. If we're in a dark room, if we turn all the lights off and close all that, and I held this burner's can up, did you tell what color it was? No, because there's no light, so you can't see. Light is an intricate part of the color we see, and we'll see it if we change the light source, it changes the color that we actually see. I know all of you love math and love that sort of stuff, so we're going to describe what we saw there mathematically. And the way we do that is we use graphs. Everybody remembers graphs in mathematics? And all that really means is on the bottom of these graphs we have wavelength. So we'll talk about it in a little bit. Wavelength is what really causes us to see certain colors, results in different colors that we can perceive. Our eyes are actually electromagnetic detectors, and they're very precise detectors in this region here that we see on the graph. That goes from 400 to 700 nanometers, and we'll talk about what a nanometer is in a little bit. Okay, and then up on this side, the left side of the graph is how much of each of those wavelengths is present. If it's the first graph, it's how much power is in the light source. So this is the first graph is for the light source, describes how much power is available from the light. The second graph there is for the object, and in this case we're talking about one that reflects light. This shows spectral reflectance. Spectral has to do with the light that comes out. The third graph is our relative response, or how our eye reacts to light. And we can see if we look up here in the middle of the graph, it's much more sensitive to light of that wavelength than the ends of the graph. That happens to be the green region of the spectrum. So we actually see green light better than we see red light or blue light. And then finally, we have the stimulus for color that represents how we see the color in our brain. And to get the stimulus, we take the spectral power distribution curve, multiply it by the spectral reflectance curve, and multiply that by the spectral response curve, and we get that. Right? Pretty simple, right? Everybody knows how to do that? Yes? No? I didn't hear anything, so I'm going to assume that meant yes. So we'll show you how to do that. It's really pretty simple. All you only have to do is multiply some stuff together. So again, our bottom axis, wavelength of light from 400 to 700 nanometers, which is the visible part of the spectrum. The left axis, depending on the graph, shows our relative power, reflectance, or it could be transmittance if we have a transparent object. Mainly we talk about reflectance. And then the third one is the relative response of our, in that case, that graph showed our eye's response. When we get into using instruments, we'll use the instrument response. Okay, the graph represents spectral power distribution associated with the light source. The spectral reflectance curve is the object we're looking at, and the response curve is the observer. Our stimulus for color, you can think of it as the perception of color, the result of the interaction of the first three. You can kind of almost think of it as we start out with a certain amount of energy that comes from the light. It bounces off the object. Some of it is reflected off, some of it's absorbed. So it's kind of subtracting the original amount of light was there, and we have less available. And then our eyes, or observer, pick up what's left, and some of that doesn't get perceived, so we end up with less. So almost think of it as starting with a certain amount of energy, and you subtract some out, and then whatever's left over is our stimulus for color. We'll look at each component individually to describe how each affects the color we perceive. Each one is important in the color that we actually perceive or see. So the first one is light. We describe that with the spectral power distribution curve mathematically. The curve describes light source in terms of the amount of energy present at each wavelength of light in a visible portion of the spectrum. The higher the graph, the more energy of that wavelength is present in the light source. Visible light is a small part of the electromagnetic spectrum. It's a form of energy, and it can be described as a wave. And so if we have wavelengths, this is our wave. We usually describe them looking like this. The wavelength is from peak to peak, or trough to trough, doesn't matter. If we measure that, that's how big, or how little in this case, the waves are for light. They're measured in nanometers, so you can imagine they're pretty tiny wavelengths of light. What is a nanometer? 10 to the 9th meters, if you've had math and had scientific notation. 1 micron is 1/1,000,000th of a meter. 1 nanometer is 1/100,000th of a micron. So in other words, it's really, really little. Okay, you can't perceive how small it is. When we look at the whole electromagnetic spectrum, in this picture, not exactly this one, but one similar to it is in your book, if you had a book. Right? This has made the visible spectrum, which is just that little spot there in the middle where it says vision, and expanded it. We see that we can see from about 400 to 700 nanometers. as far as light goes. Our eyes are detectors in that range. Now some people's may go a little bit below 400 and others a little bit about 700, but the average is around in that area. And as you get closer to 400 and 700, our perception is much less. We can see at about 550 or 555 is our maximum. And if we look on the bottom section here, we can see which colors are associated with which wavelengths. If we go to the right from a visible spectrum, where we start with the area called infrared radiation, and our eyes can't detect that, but what we do is we can feel it as heat. And if you see on TV, they show the night vision goggles where they see, not the night vision, but the heat sensitive ones where they can see people moving because of the heat from their body. That's measuring infrared radiation. Or they take a picture of your house with that and they can see where heat is leaking out of your windows, to see how good your insulation is. They're using a detector in the infrared region of the spectrum. That's important of color and putting color into plastics. Generally, we're interested in the 400 to 700 range because that's what we see. But there are some applications that are interested in this infrared region too, because if it reflects infrared energy, it keeps the material cooler. So for instance, if you made a roof with infrared reflecting pigments, it would keep the roof cooler than it would be if they absorbed that heat. So it's a way of cutting down on air conditioning, for instance. So there's other technology other than just what we see. If we keep going to the right, we get to microwaves, so we're getting longer and longer wavelengths. Microwaves, radio waves, sound waves, seismic waves. Other direction, we go past the blue and we go to the ultraviolet region. It's invisible, but this is what causes fluorescence when we have fluorescent pigments. And when you go outside in the sun and get sunburned, it's because of the ultraviolet rays, not the visible rays. So there's different kind of ultraviolet rays. But as we go this way, from UV to X-rays to cosmic rays, the wavelengths get smaller. And generally speaking, the smaller the wavelength, the more energy is present. This way, towards the left, is higher energy. Towards the right is lower energy. One way we can kind of see that visually is if you look at, say, a campfire. If we see a lot of red light coming from the fire, it's relatively cool. Hotter areas would be yellow, and finally the hottest would be kind of bluish color. That has to do mainly with temperature. So it goes from higher energy to lower energy, from left to right. But what mainly we're interested in is what's in this 400 to 700 nanometer range. And breaking it up even more specifically, each wavelength represents a specific color of light that our eyes can. We can break down that visible light. The wavelengths for blue are below 480 nanometers. Green is from 480 to 560 nanometers. Yellow from about 560 to 590. Orange is 590 to 630. Red is above 630. Purple is not actually in the spectrum, so if anybody asks you which color is not in the spectrum, purple, it's mixing red and blue light together. Violet's in the spectrum, but purple is not. White light. The fluorescent lights in this room are a kind of white light. Daylight, if you go outside in the sun, that's another type of white light. We can use incandescent bulb, again, another kind of white light. Actually, all the colors of the spectrum are added together, result in the white light. So any of these lights that we mentioned has red components, blue, yellow, green, all mixed together, and when they all mix together, it appears to us as white, because all the spectrum is there. And we can separate white light into components using a prism. You've all seen a prism? And that's what a prism does. What's another natural phenomenon that uses the same concept? Rainbows, exactly. The light or the raindrops work as prism, and they break the wavelengths of light into its individual components. And that's what you see as a rainbow. But the way it works is different color light travel at different speeds through glass. So it actually changes the speed, which changes the angle. So instead of all going to one spot, it spreads the different colors out, and then you see the individual colors. We can add the different colors of light together to get white light. Roy G. Biv is red, orange, yellow, green, blue, indigo, and violet. And that's the order that the colors go in the spectrum. Spectral power distribution. It's about the graph that shows the energy present in the light source, or call it the light curve. We have several of those lights that are commonly used in industry. And again, the left side numbers show the strength of the light at each individual wavelength, and the wavelengths are on the bottom. This is the graph for the relative power distribution for typical daylight. It's called CIE 15.2. This isn't real daylight, it's simulated. But what it shows is from, say, about 400 there to 700, you can see that there's more energy in the blue part of the spectrum in this light source than there is, say, in the yellow-red part of the spectrum. So when you look at this light source, and if we go in the lab and looked at our light booth and put the daylight on, this light source would look bluer than the other light sources. There's more blue light present in it. So the higher this graph at a given wavelength means that there's more energy at that wavelength. So the highest or the most amount of energy is in the 440 region, or 440 wavelength. And then as we go higher in wavelengths, it goes less and less and less. That means it's made up of all the spectrum wavelengths, but more of it is blue than relative to the red. So it is a slightly different color. So when you look at colors under this light source, you'll actually see different color in daylight light versus incandescent light. One way we make light and talk about light is with something called a black body. And they're kind of sounds silly to think of black bodies and light. When the body itself is cold, there is no light. And then when we heat it up, it starts giving off light. So they're hollow heated chambers where their color of the light that comes off, or the spectral power distribution, only depends on the temperature, not of its makeup. So as the temperature goes up, the spectral distribution changes. And when we describe light sources, we'll describe them by the temperature of that light source. And we'll call that the color temperature. The definition of that is the temperature of a black body producing light. And it's measured in K. And K is an absolute temperature scale. It stands for Kelvin. Anybody ever used Kelvin before in chemistry or physics? It's kind of the scientific measure of temperature. The reason it's called absolute temperature scale is that when you go down to 0 Kelvin, that's considered absolute zero. And the definition of absolute zero is no movement at all within the molecules that's at that temperature. 0 Kelvin, anybody remember what 0 degrees is in Kelvin? But 0 degrees centigrade is 273 or 276 degrees Kelvin. The degree of Kelvin and the degree of centigrade is the same size, but it just starts at a different point. Kelvin starts, absolute zero is 0. Fahrenheit is a different size degree, so there's a different conversion. We measure it in terms of Kelvin. And when we're in chemistry class and we're doing calculations that involve temperature, usually we use Kelvin as the temperature we use because it goes down to absolute zero. When we talk about black body radiation, we can use the black bodies to represent light sources. So if we have this 10,000 K here, that, if you look at that, what does that kind of look like? Probably that. Daylight? Remember the daylight curve I showed a little bit ago? Kind of went up high here and then down like that. So that can be used to simulate daylight in artificial means, this 10,000 K, although that's not the one we generally use. This 2856 one here may seem like a kind of odd number there, but what that curve represents, the 2856K, is an incandescent light bulb. If you measure the temperature of the filament in a light bulb, it would be at 2856K. And that's what the curve or spectral power distribution curve for an incandescent light bulb is. And you can see, compared to the daylight, it's much different. It's much heavier in the red end of the spectrum than it is in the blue end. So it's much more reddish yellowish light than the daylight. A couple definitions that are very close to each other. One is a source and one is an illuminant. And a source is a physically realizable light whose spectral power distribution can be experimentally determined. An illuminant is light defined by a relative spectral power distribution that may or may not be physically realized. The illuminant is the curve, or the spectral power distribution. The source is the actual light. So we can mathematically make up illuminants all day long just using mathematical tables. That doesn't mean we can actually physically make that light source. But if we say it's a source, then there is a physical entity that produces light. So that's a source and illuminant. So every source has an illuminant, but every illuminant doesn't necessarily have to have a source. Another picture of daylight. Again, we see it's higher in this part of the spectrum and drops off as it goes towards the red. Fluorescent type light source. This is called Cool White Deluxe. And you can see it's much different and gives off light than the daylight. What's the biggest difference here? What feature does this have that the daylight didn't have? These big spikes here? Only fluorescent lights have those big spikes. What's that? Peak to peak. So the shape is much different, but the spikes are the result of phosphors that are in fluorescent lights that have to do with certain chemicals. One of the ways that scientists, they'll say, we found a new star and we found out what its chemical makeup, it's, so much hydrogen, so much helium, so much whatever. The way they do that is they analyze the light coming from a star. They can pick out elements that are within that star that are burning. Usually that'll show up as spikes at very specific wavelengths. Much of that is not in the visual range, other parts of the range, but they can use spectral curves to determine the composition of anything, really. You can do it from sunlight or starlight coming in from stars, but even one of the ways in chemistry we define or figure out unknown materials is to burn it and capture the light that comes off of it and then get a spectral curve and then match it against known components and see what's in it. Expensive equipment, but it can be done. Now, this is a high-pressure sodium light. Anybody have high-pressure sodium lights where they work? They used to be real popular back in the last energy crisis, if those of you old enough to remember that, back in the 70s, remember? Parking lots is a real good place. And the reason for it is they're very energy efficient. But if you look at the curve, most of the light is kind of in the yellowish, greenish range. There's not much energy here. It's very bad for using for color matching, for instance. Like if you had an apple and you held it under one of these lights, there's very little red wavelengths of light in it. It wouldn't look red because there's no red to reflect. So it looked kind of greenish. Very specific wavelengths are there and other ones aren't, so it looks much different if you look at things under it. If it's in a parking lot and you park your car under there, the color of the car is going to look a lot different under that light at night than when it was when you parked it in daylight. Kind of energy efficient light, metal halide. Again, it has a lot of spikes. Not as we don't use these generally for color matching, but they are used for lighting areas. Illuminant A. We'll talk about the CIE and what it does, but it specifies an illuminant A. This is that incandescent light, 2856 Kelvin light. It goes like that, and that shows the curve for that. And these are CIE illuminants, standard illuminants, if you will. D50 and D65 are the most common daylight equivalents or daylight lights that are used in light booths. The one we have in our light booth is D65, and that's this one here. And if you notice, it follows pretty close to what we had for the average daylight, if you want to call it that. But there is a D50, and C is sort of in there also. But these are used to approximate what daylight looks like. It's not exactly it, but it's close. Something called daylight fluorescent, and there's lots and lots of different types of fluorescent bulbs out there.